I think I am.
I don't hear anything, but it works.
Supposed to.
I don't think we're supposed to hear anything.
I think you know that someone in the back room now goes, ha ha ha.
Okay. Maybe this is the case.
I'll need a shower after this.
So you're gonna be extending into nonlinear elasticity amongst other things.
Tomorrow.
Tomorrow. Okay.
Tomorrow it's going to be geometric nonlinearities, and I'm going to do all the elasticity of residually stressed bodies, surfaces, 3D, everything of that sort. Today is going to be primarily examples and Riemannian geometry, just geometry.
Okay. Okay.
Watch out.
Okay, so we can probably get started with our first afternoon session, and it's a pleasure to introduce our third lecturer, Efi Efrati, who joins us from the Weizmann Institute in Israel. He's going to be telling us a lot about geometry and its interaction with elasticity, and the choice of topics is sort of very, very fortuitous. He's one of the world experts on chirality, handedness, and the interplay of elasticity, geometry, and chirality.
Everything after that is like downhill. Thanks, William, for the opportunity. Thank you. It's a pleasure to be here. It's actually an exceptional setting for talking about elasticity of frustrated bodies, because the setting between the previous lectures is going to essentially set the frame for what I would like to talk about. But we'll get to most of that tomorrow. Today, what I would like to do is set the ground for tomorrow, which is, if we're talking about geometric frustration, we need to understand how to treat that quantitatively, and the method of doing that is by using Riemannian elasticity and just the geometric Riemannian framework, which is what we'll do now. So my lecture notes are online. If you have any questions or find any mistakes, this is my email. Feel free to write me directly. We're going to discuss primarily today geometric frustration. And we're going to start by considering examples. And after we've seen enough example and have somewhat of a feeling of what is geometric frustration, we will do some of the Riemannian framework. And then we'll use the Riemannian geometry framework to see a few things. Amongst others is inevitability of frustration in physics in general and in elasticity in particular. The notion of geometric frustration is, I think, takes a great role in soft condensed matter systems, and that is because the constituents of the matter we work with are big enough to have intrinsic structure. They have their own tendencies. We can associate them with things they would like to do. And the minute your constituents would like to do something, and then they have to orchestrate that in a body as a whole, that can give rise to frustration. And to make what I just said less vague, I want to consider a few examples of frustration. So I think the most famous one is that of map projections, for flattening of the sphere. We all know that if you just take an arbitrary, or this is actually the Mercator projection, one of the most used projections for a globe map. And you can see that Greenland there is way bigger than Australia, although in real sizes, this is what it looks like. And this is a flaw not only of this map, but of every map. And we know that every map would have to distort because we're taking something which is spherical and projecting it onto a flat sheet of paper. One of the most, with the least distorted maps commonly used is this thing. Hopefully towards the end, we'll be able to understand why do you need to insert all these cuts. Why is that a better strategy than using, for example, an ellipse or things of that sort? So this is something we know we have to make compromises. And by the end of this series of lectures, I hope we are able to quantify how much compromise do we need to make. Can we concentrate it? Can we spread it out? All these different notions. So this is a really common type of geometric frustration, taking a sphere and flattening it down.
What was the motivation for the asymmetry between the northern and the southern hemisphere for the cuts?
I would believe it's just to make the continents contiguous, but I'm not sure. That would be my bet. There was another question.
If I just take a globe and then
say what?
Say a globe, like
Okay, yes.
and just try to flatten it out, how it just naturally goes to this shape.
Not this one. This is very asymmetric, and I would believe it had to be a very special globe. If you will do it and you carry out this experiment, I guess that towards the end, I believe together we could figure out what it will do. But it will probably try to do something along these lines. It would add certain cuts distanced a certain distance apart, which will be determined by how much curvature, which is how much frustration it had when it had to be flattened down. Now, everything I'm now saying is assuming your globe is somewhat elastic. Otherwise, you would need to introduce infinitely many cuts in order to flatten it completely.
So there are some parts removed from the sphere?
No. Essentially, this is this showing everything? I think it is showing everything, and I think no parts are removed, but obviously distorted. This is another example. This is a Bohemia seed pod, and we're trying to study its geometry and trying to figure out what makes it do what it does, or exactly what is the architecture driving what it does. And what it does is this. This is actually a time lapse of the Bohemia pod drying up, and you see that it twists up and curls outwards. And this one is actually empty. I rehydrated it and dehydrated it to make this movie. What it does in nature is it has all the pods in, all the seeds inside, and it gradually dries up, and it stays tucked in. And it is very charged, and would like to snap open, and it just accumulates tension inside until the time comes and just disperses the seeds, and it can throw things up to 50 yards or so. So this is a very efficient machine. Trying to understand the machinery of this. Well, what happens here? Turns out the architecture inside is very simple. It's a bilayer. It's a very simple bilayer. It has cellulose fibers oriented along one diagonal on this direction, and on the other face, it has cellulose fibers oriented along the other direction. And when it dehydrates, essentially each of the layers shrinks perpendicularly to the direction of the scaffolding. So this is essentially very stiff. It doesn't shrink in this direction, just does this and this. You can mimic it by taking two rubber bands, tensing one rubber band along this direction, the other rubber band along that direction, and gluing them one to the other. And then when you do this thing, you can cut it out and see what it does. Let's build about on Alex's lecture about bending. So this is one cut. I'm taking the cut now along this direction. Along this direction, here is my bilayer. This was actually wrong. On this direction, when I take it out of the frame, the upper layer would like to shrink. So what I'm doing is essentially I have this somewhat shorter stubby rubber band, tensed and glued to the longer one. What it would like to do is it would like to induce this kind of curvature. If I, however, take the upper cut, the vertical cut, what happens is I have originally two of these, and the lower one is tensed, so when I release it, it would like to shrink. So the lower one looks like this, and what it would like to do is to curve along this direction. We can try to quantify by how much would this thing like to...
3 and 4, the one you referred to?
No, I'm talking, no, neither. So these belong to a different figure. I apologize for them being there. So yeah, so I'm doing this cut, and it would like, what we just realized, if you take this cut, you'd see it would like to buckle that way. And if you take one of these cuts and just look at the side, it would like to buckle this way. So this is what every point in space would like to do. And we would like to now quantify these curvatures based on what Alex just taught us. And what we do is the following. We say that there's the neutral surface at some radii r, and this is one thickness apart, and this is one thickness apart, and say this has shrunk by, let me just be consistent with my notes, this has shrunk by a factor r times 1 minus alpha over 2, and this is 1 plus alpha over 2. So this guy is longer by a factor of 1 plus alpha over 2, and this guy is shorter by a factor of 1 minus alpha over 2. That's all that's happened. And now when we do this, we have L out over L in, that's R plus T over 2. We can multiply it by delta theta, but it's going to cancel out. We can do this. And L in is R minus T over 2 times delta theta. And this also equates the strains. It's 1 plus alpha over 2R, and it's 1 minus alpha over 2 times R. And what these two all give us is that kappa, the curvature, which is r to the minus 1, equals what is the only thing that has dimensions of length here, except r, t. Alpha over t. That's it. Okay? Now,
T is the total thickness of the distance to the neutral surface.
yes. Now, thank you for pointing that out. What I did is, I mean, you can't really say that this has the same lateral thickness across throughout. So I did another averaging, and I associated the strain with the middle of this layer and the strain with the middle of this layer. This is why this is t over 2, and this is minus t over 2. So I sort of say I prescribe the length of this guy on average, the length of this guy on average, and then I get a curvature. Now, the reason I did this exercise is not to show you that you can get this thing as an alpha over t, but to say that if we take this thing and make it thin enough, we can keep the same curvature and use arbitrarily small strains. Okay? Now, that is going to be important because I would like to say, well, what happens to the 2D geometry of this surface, this thing that forms a helicoidal ribbon-like object? I can get something which is originally flat to have two opposite curvatures while using arbitrarily small strains. But it kind of contradicts what we know, that if a surface is curved along two directions, then it has something which is called Gaussian curvature. We're going to introduce that in a minute. And it can simultaneously be flat with no strains and have a Gaussian curvature which is non-vanishing. So this is a type of surface which would like to have curvatures that cannot be realized by its own geometry. What we will see further down the road, probably tomorrow, is that it chooses a smart way of compromising these two tendencies. Questions so far?
What was alpha again?
Alpha is the shrinking ratio. So I tensed this with relation to this by a factor alpha. So I tensed this by alpha over 2 and contracted that by alpha 2. It's the strain. It's a dimensionless number, yes.
And the fact that your lovely model system was cut up into individual rubber band strips is just irrelevant for the argument. You had solid sheets of rubber and you pressed them, as in the upper right, same thing with that.
Yes. Actually, thanks you again. We will see that the different strategies of resolving this frustration depend on how I cut it. If I cut a big chunk or a small chunk, the strategy for resolving the frustration is going to be different. Okay, next. Okay, so this is a nice little game. It has less frustration, and it is not an impossibility, but a breaking of symmetry. I have n cells. At every generation, n cells produce lambda n cells and deposit them on top at a distance h, which is the typical size of a cell. Say lambda was 1, then I have n cells and n cells and n cells and n cells and n cells. I construct a cylinder. Now say lambda is bigger than 1. I have n cells and lambda n cells and lambda squared n cells. So not only my circumference grows, but it grows at an increasingly growing rate. You can quantify this geometrically. We'll see that also later. It's actually a shape of constant Gaussian curvature. It's called a pseudosphere. As this thing grows, we can ask the question of how much further can the next ring be? Say I have a circumference r. The next layer of cells is going to be a distance h away. That's the diameter of a single cell. And it's got to be longer. Okay, if I put it directly above me, it's not going to be any longer. If I put it inside, it's going to be shorter. The further out I put it, the longer it can be. What's the longest it can be? What is exactly? So say I have circumference at stage t, or at a generation s, plus h. So I have s times h times a single cell, and then I add one more cell, and I say what is the circumference of that minus the circumference of just the s generation. The most this can be is 2 pi h. And you get 2 pi h if you go directly out, planar. So if you hit the horizon, if you hit the plane, I just told you this trumpet shape opens up at an increasingly growing rate. It's going to hit the horizon sometime. And this is called the horizon of the pseudosphere. We can show that this has a curvature divergence here. Something pathological happens. What we care about is the fact that the cells growing there don't know differential geometry. They have no idea that there's something global interesting happening here. And then they have to find some resolution. So they would like to grow at an increasingly growing rate, and they have to accommodate it. One of the strategies of resolving these kind of things is doing these. So you have to break symmetry. But it turns out that in these particular types of problems, you have to break symmetry all the way in your shape. Yes, it would introduce a scale on which you introduce strains and then forget the area increase law. The claim that this has to go all the way down assumes 0 strains, which will be relaxed then. It could occur just on a finite thickness. So this is it for these. And yes?
Sorry, maybe I wasn't quite following, but is that more than just theoretical coefficient? I mean, do you have like cells that actually do something like that?
Yes, and if we had a daffodil out, I would show you. So we can be sure that the daffodil exactly does this, but I'll show you other examples of plants which we're quite certain that this is their growth strategy. I want to not get into it deeply today because that's a big part of tomorrow. It worked. The last example I want to give is belongs to the field of liquid crystals. So when we deal with liquid crystals, specific pneumatic liquid crystals, is there a light here?
There's a console to the left there. One of them might work.
Hallelujah, thank you. We quantify everything by a director field, which essentially counts the local orientation of the underlying constituents. And in the case of pneumatics, which is what I would like to talk about now, we should think of things as being roughly rod-like objects. And this would tell us what is the average orientation in a given place in space. Now, it's true that everything would like to co-align, but then we can give things defects. We can give things exotic boundary conditions, and then things would have to distort. And we pay energy for this distortion, and we pay it in the form of the Frank free energy. And the first two terms, is there a half here? There is a half. The first term is called the splay term. Okay? It penalizes splaying of the director. It's important to understand that this is not to be understood in the standard dilational sense we're used to from electrostatics, because it doesn't get any thinner, it just splays in orientation. There's another term which is called the bend term. This term essentially would like to account for this kind of a distortion. How do you do that? What? With curls? That doesn't look like a curl. And so there's a way of using what you said. I would like to pursue a different way, which is this is essentially a changing in the orientation along the director direction. So I found commonly you find your definition, but I found this more intuitive. Differentiate n in the direction of n and square that. So that's the bend term. In 3D, there are two more terms. One is divergence of a function, which is called the saddle splay. The other one is called the twist term. Both of them are in the notes. I don't want to get into them here. But we can essentially say, let's call the splay S and the bend B. Then this energy is S squared plus B squared. Okay, it's a quadratic form. It's not extremely interesting. But then we say the constituents could have internal structure. What happens if they're not that straight? What happens if your nematogen, the single constituent forming the nematic liquid crystal, has a small bend to it? These are called bent core liquid crystals. And you say, the next guy would like to do something along these lines, along these lines. And even if the bending of an individual molecule is minute, you're going to accumulate that, and you're going to see that. And if I go along the splay, doesn't matter. This could essentially be tangent. But if I go along their direction, they would like to rotate their orientation relative to one another. I would like to say that the continuum description of this guy is this. It has a reference bend, an intrinsic tendency, want to do something, but otherwise it would like to have zero splay. Now this is where things begin to be interesting, because we would like it's tempting to say, well, you know what, the ground state is going to be 0 splay, bending equals bending not, and you're done. What we'll show next is, guess what? There's no such configuration. How do you do that? And this is going to be the key, and almost everything else we're going to do is going to follow these lines. It's going to be constructive. We're going to try to construct the field that has 0 splay and B equals B naught. We're going to start by saying n is cosine theta sine theta. And theta is going to depend on x and y. And splay would be dx cosine theta plus dy sine theta. Bend is going to be a bit more interesting. It's going to involve taking n dot grad, acting with that on n, which is a vector by itself, squaring that, and then taking the square root. Okay, so it's going to be completely different from this guy, but with not much algebra. Do I have it here? I actually don't. We shall just have to do this. Okay, it's cosine theta theta x plus sine theta theta y.
So it's a little counterintuitive to me that you have a. I would have written down p squared minus p naught squared rather than p naught. But it seems like there's no directionality. I can rotate the molecule and go up rather than go down. For every one of these configurations, I could have a configuration bending up rather than down.
I agree. So this has already rotational invariance to it. So this guy doesn't care if it's this way, this way, or that way. I think what you're saying is that if now I make a defect of this sort,
You will have different energy.
then the energy contribution, which is different, is going to be accumulated just in the splay term. And in that case, you are correct.
I'm saying those two things are not energetically not equivalent, where I would expect experimentally, physically they're equivalent.
Okay, so here comes my cheat. B, as I calculate it, is always positive. It's not a 2.
Absolute values.
So it's an absolute value of a bending.
We
Yes.
played around with energies like this, but we always took it to be b squared minus b naught.
Yes. When you come to construct it, it will also say that B, if there's 0 splay, it would say that B has to be a constant, either plus or negative, but it can arbitrarily switch.
One way to understand is like you're expanding around a particular minimum of my theorem, which has b squared.
Yes, could be. Yes. The way I do this B is essentially take the square root of this, so it's always positive. So I don't have the ability to change sign. So this guy is synonymous with yours under this definition. Okay.
Sorry, there's going to be this is a 2D pneumatic, so there's no escape into the third dimension.
Yes.
allowed.
Yes. And what I'm doing here, it's just this. There's no other way. And it turns out that up to a sign ambiguity, which I was corrected for now, everything that's written up there, which means take this n, contract it with a gradient, take the derivative of n, square the whole thing, take the square root of that. You get this for a b. So this tells us, and this is, of course, for display, it's a minus sine theta, theta x plus cosine theta, theta y. I apologize for writing in the shadow. This is actually not mobile. What we should take from these two lines, though, is that 0 here and b here, theta x, theta y, theta x, theta y. We may invert this thing and get an equation for theta x and theta y. Now one of them is a cosine and the other one is a sine. Theta x is b times cosine of theta, and theta y is a b times the sine of theta. Okay, so far what I have assumed is that b is a constant. I actually haven't had to assume that yet, but I will soon, and that s equals 0. That's my assumption so far. And lo and behold, you got a differential equation, a partial differential equation. Why do I say that this leads to frustration? Is because this does not always define a theta. When does this define a theta? When they're compatible. When what? Yeah, that's b0. Yes, it's the constant b. Yes, thank you. These two are compatible only if theta xy obtained by taking this derivative equals theta yx by taking this derivative. And now we can do this. Taking theta xy gives you b naught sine theta theta x with a minus, and theta x theta y, thank you, and theta y is a sine. So this is essentially minus b naught squared sine squared of theta, and this should be equal to taking the x derivative of this, which is b naught cosine theta theta x by this thing is b naught cosine theta, which is b naught cosine squared theta, b naught squared cosine squared. And this doesn't happen except for a particular theta. And if you're stuck in a particular theta, then your bending is 0. So this can't really happen. And what we will explore in the upcoming sessions is, what does a system do when it has an intrinsic tendency, such as this, that cannot be satisfied on the global scale? This has the choice of either varying b or introducing a splay. And in the third dimension, it could also introduce a twist in order to absorb these things. So as we see, and this is going to be the key, we're going to get very exotic behavior from very, very simple input, provided that the input cannot be really satisfied in the most trivial way. Yes?
Just as a comment, this system has in fact been recently realized by Noel Clark, where they have these helicoidal states where spontaneously expresses a twist to resolve it.
Yeah, so this is a very big topic here at Boulder, studying optical activity in bent core liquid crystals, which is something that is naturally chiral, but comes from a non-chiral state, which exactly has to do with the resolution of, you just give me a bend, and the best game in town to realize a normal bend is to add a twist to it, and that twist manifests as optical activity. Yes, so this is an exceptional good place to talk about these things. Okay. So this concludes the section of the examples and what are the different notions of geometric frustration I would like to talk about. And now comes the time of the formulation. So how should we understand all these different examples in terms of geometry? So as we saw, the major tool of Riemannian geometry is the metric. So we have to go through some tensors, and we have to go through some notions of covariant calculations and contravariant calculations, which is never pleasant. But we're going to do this in the context of embedded objects. We're going to do this in the context of surfaces of embedded 3D. And it's going to make things much more simpler for us because we're going to have intuition for them. Bear in mind that everything I'm going to do is much more general. You don't have to have an embedding in order to do the things I do. It's just more convenient to think about it this way. Riemannian geometry is the field in geometry that essentially asks how far can you push understanding about a geometric structure only knowing how distances behave in the structure. Okay? In particular, if you have a manifold and someone tells you, oh, that direction is up. And in every place on that manifold you can say where is up. That's not a Riemannian structure. That's an additional structure on top of the Riemannian geometry. The Riemannian geometry by itself cannot tell you directions. It can only tell you distances. And therefore, the central tool is the tool that tells us how distances are measured. If I have a solid, and when I say solid, essentially what I mean is I have some coordinates, and I map them into our space. And then I want to ask how are distances measured in these coordinates, in this space with respect to these coordinates. ds squared, I get the following. I get dr dxj internal product with dr dx I dxj dxi. So I take the internal product of R. This was called on the previous lectures as the deformation gradient. And this is what we call the metric, Gij. It's important that I'm using lowercase indices because I'm differentiating with respect to uppercase indices, and this is always going to be the case. An exceptionally useful notion is the inverse metric, Gij with an upper index. So this is the only case where getting the indices up is going to change the whole meaning of the tensor. And Gij is defined as the tensor which when contracted with Gjk, so Cj appears here twice, you get a delta Ik. So this defines the inverse metric. Now that that was defined, every time you give me a lowercase vector, Vk, I can construct from it an uppercase vector by using the inverse metric. So from this point onwards, it doesn't change the meaning, it just does this thing. What is this vector property? How do we treat vectors in Riemannian geometry? Well, what I really mean, if we think now for this embedding, for a mapping from X into R, then the vector is a vector in R, but I want to express it through the X's. So what I do is essentially write that a vector in the space R is essentially a few components. These are the contravariant components of V, and they multiply, let's do it Vi, and they multiply dir. Lower index I means it's dr dxi. That's okay. This is a vector in our space, and these are just the weights of the different vectors. Every time I tell you these are the contravariant components of a vector, you should think of these coefficients. Okay? I'm not telling you all the rest, but these are what determine the direction of this component on the manifold. Similarly, I can write the same vector in its contravariant, in its covariant components, which is going to read vi gij dj r. Okay, so essentially doing this kind of takes this index up, or you could think of this as retranslating this. So now these are the covariant components of this vector. Yes.
Why are we taking derivatives as the R vector versus?
Oh. R, or the domain in which R lives, is where we live. When I tell you I want a vector, what you should think of is a velocity vector of a particle moving in the domain of R. That's what I'm looking for. I'm looking for a velocity vector. And that's on the one hand. But on the other hand, I want to formulate everything just by knowing X. I want to do everything that I can in my power to formulate things that live in R, but I want to do that using the language that lives in X. And that's my limitation. So this vector lives in R, but I want to express it through components that care about X. And in particular, when I'm going to ask how things change now, I'm going to do it in the domain of X. Every time I'm going to differentiate, I'm going to differentiate with respect to X. Yes, it should be thought of as curvilinear coordinates, nothing more than that for the time being. So let's do that. Let's take a derivative. Say I want to do djv. So I'm taking the vector that lives in R and I'm differentiating with respect to xj. What I'm actually doing is I'm doing this. I'm taking dj of vi dir, which is dj vi times dir, plus there's another term, because in the next place I'm examining, so a differentiation is naturally examining 2 points correlations. In the next place, dir points in another direction, could be different in magnitude. This correction terms is exactly vi dj dir. Now, what we could do is say this guy is defined to be the Christoffel symbol. Now what is this? djdir is a vector. It lives in the domain of R, and we say, well, you know, we have 3 tangent vectors in R. We can express everything in terms of those 3 vectors. This is what we do. Commutativity of differentiation with respect to X in the domain R, everything is normal, nothing is curved yet, maps to the fact that the Christoffel symbol, this object, is symmetric with respect to I and J. The last portion we care about is now making everyone have the same indices. This is djvi. This was vi gamma ji k dkr. I'm going to swap k and I such that this guy, the one who was I, is going to be k. The one who was k is going to be I. And everyone is going to multiply dir. So this little maneuver, essentially some index gymnastics, is allowable because we're summing over these guys. We're summing over these indices. Their name doesn't matter. What this told us is that if you're trying to differentiate a vector, you had better take into consideration the fact that the basis vector which you work with change their direction and magnitude in time. So you have to have an additional correction term to your vector. The R define your basis locally. They're the local tangent space. And then these guys tell you how to cope with it. Okay? From this point onwards, if we can do all the algebra we can while omitting the specific vector, then we can just amend the way we do differentiation and use it that way. So I think that's a good place to have a small stop. Do you have any questions for now? Yes.
Why would you want to take the derivative of your vector with respect to the
Two things. Very soon now, R is not going to be existent. Second, even if R is going to be existent at some stage in time, it might be part of the solution. I wouldn't know what R is to begin with. Whereas I know, choose any parameterization, and this is a freedom I would like to have. I want to have any parameterization of my object and be able to do things with respect to an arbitrary parameterization and then carry it on. And last of all, very soon, we'll see that we're going to end up with a bunch of definitions that have no R in them. As a matter of fact, they're going to live without an embedding. The reason I'm doing it with an embedding is because it's more intuitive. But everything we'll get around to is generalizable to a non-embedded metric. So it's a geometrical structure which can live by itself, and then we can ask questions about that. So let's have a 5-minute break now.
So in terms of thinking about R, I can really just think about it in terms of your definition of the displacement in the space. You were defining
There's no displacement. No displacement. There was just a mapping. You started at X, you went into R.
Right.
This is how you measure distances. It doesn't say displacement.
Oh, that's what I meant. I mean, I can think of the R as simply being defined in terms of how we measure displacement.
You can go ahead.
Can I see the other board for a second?
Because I mean, I've learned these before, but I think I might be just missing, because you said we're about to become agnostic to our parametric parameterization, or however we're parameterizing this vector.
Yes.
Because I think I learned all of this without ever having R's.
Because that's the more correct way of doing it.
Okay. So just
that's the more correct and more general way of doing it.
Okay.
I'm doing this because I was told a lot of people don't have backgrounds here.
Okay.
And then we'll do this, and soon enough we're gonna go to Riemannian manifolds that don't live in 3 space.
Right.
And then once we get to them, then everything else is game. Okay.
So prescribing each R provides a deformation of this manifold, right?
Providing what?
If I put it in the language of what Lubensky spoke in terms of the target manifold and its embedding into real space, is what is provided by R, right?
Sort of. And what you'll see is we'll have yet a third object. Okay?
Oh, yes.
Very soon now, our reference state is not going to be given by the coordinates, by X.
Okay.
What you're saying is, X is where I want to be, and then I am going to R. And then this is a deformation.
But then the X is just coordinate charts, right?
It's a coordinate chart. It's going to be completely arbitrary.
Yes.
And we're going to use that to define where we would like to be and where we'll go. Okay?
Just a question. So normally when we define like covariant versus contravariant coordinates, I used to think about them as like different transformations. They have different rules for transformation, like from the metric tensor. What is the physical intuition here, which we have 2 different set of?
The fact is that there are 2 spaces.
Yes.
The space of vectors and the space of covectors. Okay? And in order to construct a scalar, you have to use a covector and a contravector.
Dot them together.
That's the only thing. So the contravectors is the space of what are they called?
Vectors.
Of they're the dual vectors. They're the functionals for vectors. And once you get that, then you can essentially think that nothing which is not a scalar has a reason for living, and all the rest is details.
So
And now if you do a vectorial equation, then they all have to be of the same kind. The reason being because you're going to only make sense of it contracting things. And you can contract only if they look the same.
yes.
So when we eventually measure things, we only want to measure scalars.
Scalars, yes.
And we do that by carrying in my pockets, a few contravectors and then contracting them whatever I have.
The intention is really similar to what GR does.
Yes. Yes. Okay.
Have you seen these experiments?
Of course I have. I've talked with Noel about 2-3 years ago. So when I've learned from him and from Jonathan Salinger about the flexoelectric effect and a whole host of things I was never realized.
This is something else.
What I'm talking about is the back-to-back science papers he had a good few years ago.
Yeah, no, this is not it. These are new ones.
Okay.
It's not the bananas.
Okay.
It's the ones that have flexible link. Actually, there are two hard rods, and they're connected by a bond which is flexible. So they form these helicoidal phases. So these are within a year.
Yes, I was making these notes, and Jonathan Salinger was visiting in Israel, and he just is a month ago. And then I got this thing, and I'm giving them homework to calculate the compatibility conditions for splay-free bend. And it goes like, that's not in any textbooks I know. Like, really? There's no compatibility equations for these things? And he says that as far as he knows, there is none. Like a differential condition relating S and B. It just blew my hat off. I was like, I'm scribbling this down, as study notes for these kids, and it's just to teach me how, when someone which is external to a community comes and think of things that belong to something perpendicular, it just
different way of looking at it.
Yes, please do.
So when you define the covariant derivative in your space, are you defining it as a derivative with respect to physical space or with respect to the base space?
Base space. All I have in my pocket is X's. I don't have any R's.
Okay. But
it has to make sense in the R's, but all I have is X's.
The metric that you have at least on the base space, is the metric induced from physical?
It's induced by the lengths in R, but it's written in terms of X's.
But that means that the covariant derivative of the metric is non-zero. Whereas, it's the natural, in GR at least, it's nice to
it's always zero. The covariant derivative is going to be zero.
But if it depends on, this quantity here in the X coordinates is X dependent, though, right?
It is X dependent. Its covariant derivative vanishes. Its simple derivative won't vanish. Its covariant derivative will vanish.
Of course.
So it's going to be, a trick in algebra for you to... Where do they have chalks? So, I mean, it sounds like you have some experience in terms of so define gamma as, half dg minus dg. There are three indices here. It's I, J, K, G, K, L, D, I, G, J, L, D, J, I, L, D, K, Ij, and you say, well, this gamma, and now you say the covariant derivative of the G, any, and it has two, so it's going to have two Christoffel symbols. Everything, though, is written in terms of x's. It just have to make sense in the context of the Yes.
I have a simple question. So here it says b is equal to theta x over
Divided by cosine.
So it's b0?
It's b0, yes.
Long wavelength stuff like that.
Actually, that's b. You only care that it's b0 when you differentiate.
Oh, okay. And can you upload also pictures? They're really good.
Okay, sure.
Yeah,
I will.
thank you.
No problem.
Yeah, that's right. No, what you need is you need a bed. You need a soft bed interaction problem. Okay, so just so as long as there's a twist bend coupling that you can't avoid if you don't have a azimuthal symmetry cross section. So take your belt, let's flat like this. Try to bend it like this, and you'll see what we'll do is we'll twist and try to put the bend that way instead.
Okay. So let's continue. So we define the Christoffel symbol for an embedded object as the coefficients in the linear combination of the embedding when you take second derivatives. So the del is something which we call covariant derivative, and it's going to be the partial derivative as you would do it with a compensation term that is proportional to your vector, and it accounts for the rotation and elongation of your natural coordinate system as defined by the tangent vectors. So this is the definition of the dels. This is a covariant derivative of a covariant vector. This is the covariant derivative of contravariant vectors, and both of them have gammas in them. This is a J and an I and a J and an I.
Upper right.
Upper right. Okay. This is an I. This is a J. This is an I. This is a J. This is an I. This is a J. I will choose my letters better. Thank you. Sorry for that. It would not be too surprising to tell you that if I now contract this thing with a tangent vector, say dLr on the left, I could write this whole thing as derivatives of the tensor, which I remind you was contractions of tangent vectors. This is an exercise which I don't find too interesting to do, but you could do it if you would like. This is the inverse metric. It's di g j l plus dj g I l minus dl g I j. And you get this directly from this definition. But the advantage of this definition is that it doesn't know about R. All it cares about is about the metric. So in order to be able to tell me how to correct for the motion of the unit vectors in space, is you have to know how distances behave with respect to your coordinates. So once we know that,
you also use a definition of metric that Tom defined, dr, dir, dot, jr.
So now the metric is defined as the way you measure distances. Yes, please.
Are I and j changing for 1, 2, 3, 4?
Yes. So you could have them either 1 or 2, depending on your question. If you're considering two-dimensional manifolds, you know what? They're going to be I, j, k reserved for three-dimensional objects. And if I'll ever consider two-dimensional objects, I'm going to use Greek sub-indices. But essentially, when you see indices in the literature, this summation is over all the range. If it's a two-dimensional manifold, 1 and 2. If it's a three-dimensional manifold, 1, 2, 3.
So you mentioned something about embedding two-dimensional manifolds.
It wasn't two-dimensional. It was a three-dimensional in 3 dimensions. R and X both were three-dimensional.
So how does it help in simplifying the problem? That when we embed something
I didn't say higher dimension. I said, well, if you've never seen covariant derivatives, if you've never seen these guys, it kind of helps to see them emerge induced by something you would know as a distance.
Yeah, I thought you were embedding it in
No, not yet, not yet. So this was just the same dimension. And from now on, I don't need to think of the other dimensions I have. I will in one space, in one point in time, but not much more.
Just to make sure I understand, if you're describing a daffodil, curling edge, you want to have I and j running over the two-dimensional.
Yes.
R would be three-dimensional of the flowers.
Yes, indeed, correct. And we're going to get to thin sheets embedded in 3D just towards the end of today. If I was indeed describing an embedding of a three-dimensional object in a three-dimensional space, essentially using x just as curvilinear coordinates on my object, then everything would have been Euclidean. And in particular, the geometry described by this thing would have been Euclidean. Now we want to embark on a journey that takes us to a non-Euclidean geometry, but Riemannian. So the central notion is that of the metric. And the main difference between general Riemannian geometry and that of Euclidean geometry is the parallel postulate. A general Riemannian geometry forfeits the parallel postulate. And the parallel postulate essentially says that if you give me a line in space, a straight line in space, and a point not on that line, then I can pass a unique line going through that point, which is going to be straight and will never intersect the original line. We can think of this as constructively again, as performed in directions. If I have a straight line and I have another line perpendicular to it, which is also straight, and then I emanate from this guy another straight line, which is perpendicular to the first, in Euclidean geometry, this is never going to meet the original line. To some extent, it would mean that I can transport this direction from here to here, and it would not change. It turns out that in Riemannian geometry, this line could either splay away or come closer. The case where the lines come closer is called elliptic geometry. It's going to be characterized by curvatures which are going to be positive. We're going to get to the notion of curvatures soon. And when lines, so this is straight line, straight line, straight line. You see that we have to generalize the notion of a straight line soon. These are called hyperbolic geometries. Obviously, if I now try to take a direction, say this direction, and ask where does it point, if I advect it along these straight lines, it's going to point in different directions. In particular, I can take a small loop composed only of straight lines and try to take a direction and keep it at a constant angle with those straight lines and follow the different segments and ask, well, what happens to that direction? In Euclidean space, that would be trivial. In Riemannian space, taking the difference between these directions essentially amounts to taking the second derivative of a vector in two different ways. So you ask, how does a vector ij vk change when I take it along this path, I first and then j, versus j first and then I? This is going to be proportional to v. And the coefficient of proportionality, which is going to have, except for the index L, 3 more indices, so it has 4 indices, is called the Riemannian curvature. It tells you how to advect directions in space, or essentially how second derivatives, how non-commuting are second derivatives on your manifold. Because I'm taking the difference between two objects, and if it's a bigger guy that I rotated, it's going to be a bigger difference. But we should understand this in the context of directions and not vectors. That's why you want to get rid of the size. Okay, now this thing is something we know how to do. What do I mean we know how to do? We know what's written out there. So we can express this guy entirely in terms of the metric components. So we just substitute this into this. It's a bit boring, but when you do it, you get di gamma L j k minus d j gamma L I k plus gamma pairs gamma n j k gamma L I n minus another gamma n j k gamma L j n. One of these is an alpha. I'm going to let you figure it out by yourselves. My bet is that it's this one. But yes, but we're gonna sort this out later. Sorry. Okay. There's no alpha. No. Yeah. So I was simultaneously translating from alpha to ijk, but I had two i's in there, and I was an alpha. So yes. Yes. Okay. Yeah, and all of this is multiplied by v. Yes. VL. Okay. What I want to do is take all these structures we just learned about and say, well, what good do they do us? The first thing to note is that we can use this as the definition of the Riemannian curvature tensor. And this means that from this point onwards, we have no R's anymore whatsoever. We know the metric. We can derive from it the Christoffel symbol. We know how to differentiate things. We know how non-commutative second derivatives are. That means we know everything about the system. We can only make sense of scalars, and scalars are obtained by contracting covector and contravariant vectors. So we better make sure that whenever we write an equation, we equate components that have similar properties. One word of caution is that gamma, Christoffel symbol, which appears here, is not a tensor. It doesn't obey tensor transformation rules. It doesn't behave the same way as G does, or as a product of two velocities, or three velocities in the case of a three-indexed object. The difference between two Christoffel symbols is a tensor. It's a subtlety. If you have two different metrics you're juggling around, and you want to take the difference between two Christoffel symbols, you generate a tensor. A derivative of a vector, the partial derivative, does not give you a tensor. The partial derivative corrected by the Christoffel symbol gives you a tensor. So all these things are things we have to keep in the back of our minds to make sure that we always work with things that are well defined. So once we've said that, we want to come and ask, well, what are the properties of Euclidean space? What are the properties of non-Euclidean space? In Euclidean space, every two derivatives commute. In particular, the parallel transport is trivial. That tells us that all the components of R have to vanish. If I describe an object which is in 3D, Euclidean space. This is a body with Cartesian coordinates on it. Now say I can induce some differential growth. Every point in this object is going to grow isotropically by some factor lambda, probably lambda squared, where lambda could be a function of space. But note that the growth in all directions is the same. What would give you such a growth? Thermal expansion would give you such a growth. If you're a plant and you grow by softening your cell walls and the work is done by turgor pressure, you would expect this kind of a growth model. And many other systems also would obey this thing. And we want to ask the following questions. What lambda gives rise to no frustration? No, it's just you can consider a specific lambda. It was a whole process, and I'm just taking the final lambda.
But I can think of it as before and after, as a result of a bunch of cell divisions.
Yes, for example. So cell divisions could be oriented, but cell expansions would be something more isotropic to think of. So there was a finite process. It took some time, and this is a function of the Lagrangian coordinates, of the cell identities I had to begin with.
So if you were to osmotically shock a bolus of cells, it would swell, and the result would be some lambda.
Probably so, yes, indeed. So this is the process. And it seems like something reasonable to do. And when I'm saying no frustration, I mean I can realize this metric in our space, in our world. That sounds like nothing which is too much to ask. Yes, exactly. And to make my algebra later somewhat simpler. Riemannian curvature tensor, it's not that trivial to show, but has 6 independent components. In 3 dimensions, we have 3 times 3 times 3 times 3 components, but not all are independent. It has lots of symmetries, lots of anti-symmetries, and when all the dust settles, it has n squared times n squared minus 1 over 12 independent components. If n is 2, then we have 4 times 3 over 12. It's just one component. It's called the Gaussian curvature. And if n is 3, then we have 6 independent components. We take G equals lambda squared times the identity. We calculate all 6 independent components of the Riemann curvature tensor for it, and we get twice d1 lambda squared minus lambda d1 lambda minus Laplacian of lambda equals 0. And there's another equation, minus lambda d2 lambda minus Laplacian of lambda. There's another one. Note that everything has to be symmetric with respect to all coordinates because the process itself was symmetric. And we have 2d1 lambda d2 lambda equals 2d1 d1 lambda d3 lambda equals, and twice d2 lambda d3 lambda, and each of those is going to be equal to minus lambda d1 d2 minus lambda d1 d3 lambda and minus lambda d2 d3 lambda. Okay, 6 independent, very, very ugly equations. Turns out they're not that ugly. You can take linear combinations of them. So this is not directly what you get from R. This requires perhaps 2 lines of linear combinations, but you get this form. And when you take this form and you try to solve it, it turns out this thing is completely integrable to within 2 constants. So you do some gymnastics, and those of you who wish to do some, this would be one of your home exercises, one of the more tedious ones. But you get the following answer. It's a very compact answer. Only if lambda has the following form.
Can you remind me what delta is in these equations?
Delta is just d2. It's just the Laplacian.
Oh, okay.
d1 squared plus d2 squared plus d3 squared. It's the standard Laplacian. Only if lambda has the following form: some positive constant over x minus x naught squared. We ask a very, very specific question. What type of an isotropic growth profile does not result in frustration? What type of growth profile corresponds to a body I can embed in my space? And the answer is this, and no other.
So you're asking for realizable deformations, but they're not flat.
These are Riemannianly flat. In order to realize them in our world, which is flat, they are Riemannianly flat 3-dimensional configurations. Yeah, to avoid frustration, you have to be Riemannianly flat, and in this context, it's synonymous. If you're a mathematician, then you can say, well, of course, you know, the only conformal mapping in 3D are inversions of a sphere. But if you're not, it's kind of surprising, because it tells us that if we undergo something which is rather intuitive, chances are we're going to end up with something which has no embedding in our world. And this is most deformable bodies. They end up very fast with something that has no realization. And this is what we should take with us when we consider these objects. So there, things become much, much less restricted. There are many, many such embeddings. Essentially, every conformal map would give you such an embedding and get lots of freedom.
But still, some random biological process.
A random biological process.
Cells in a plane, are they going to be able to discover a conformal map?
It's a question of, are these bacteria smart enough to solve a log Laplacian? The way to formalize these things in 2D, so thank you for mentioning this. In 2D, we can ask what happens. It's nice to put it in the exponent, not because it's meaningful, because it's, again, simpler to write things later on. It turns out that you have to satisfy this equation. Note that lambda here is in the exponent. That's why I said it's a log Laplacian. And only if it satisfies this, then can it start with a flat 2D configuration and end up with a flat 2D configuration. Okay, so this is 2D world going back into 2D world. There are many such functions. Not so many these kind of functions. Okay. The last thing I want to get around to for today is talk about embedded surfaces in 3D. Okay, so there's nothing very special about embedding surfaces except that we're going to treat thin bodies, and then we would like to know how to treat them. So they're not interesting from the Riemannian point of view, but they're going to be very useful. When we were looking at the Riemannian structure of 3D bodies, all we had is the metric. Now we're going to take a two-dimensional manifold, a surface, and place it in three-dimensional space. Okay? It's going to have two entities. So now R, our vector, takes us from the domain omega, which is in R2, and brings us into R3. So it takes two-dimensional patch, and for this alpha, beta, gamma would only range between 1 and 2. And everything we're going to do is we're going to do that with respect to two-dimensional coordinates. So we have two-dimensional coordinates, but the image now lives in three-dimensional space. If I give you the metric, I'm going to use A for the metric of two-dimensional bodies, and we could think of that as d alpha r. R lives in 3D, taking the dot product. Now 3D is dead. All I have is the two-dimensional indices. Does this prescribe the way the surface lies in space? What this prescribes is how distances behave on the surface. Can I change the conformation of a surface without changing distances in the surface? It turns out that the answer is yes, and you can change it by changing its curvatures. There's another tensor, which is called the second fundamental form, and we obtain it by considering second derivatives and dot producting it with the normal of the surface, where the normal of the surface is just the cross product of the tangent vectors. So you have a surface, you look at the normal to the surface, and you ask, what are the curvatures? What is the second derivatives on my surface normal, projected to the normal? Now, if I give you an A and a B, is this enough? Did I prescribe a surface? Did I prescribe the conformation of a surface uniquely? Do I need something in addition? Have I stated too much?
This is beyond translations and rotations.
Beyond translations and rotations, yes. So modulo the trivial degrees of freedom we mentioned earlier, modulo translation and rotations, are these enough? Can I always achieve such a surface? So again, you can think of a constructive proof. I give you an A and I give you a B, and you try to build from that a surface. And it turns out you can't always do that. A very elegant proof goes along the following lines. It says this. Say I have a surface R of x1 and x2, and now I want to thicken it in 3D. So essentially, I go along the normal to the surface, and I go a distance x3. So now I have a solid, which is a function of x1, x2, and x3, and it's made out of taking your original surface, 2D, of x1 and x2, and extruding it along the normal with the coordinate x3. Okay? So the normal is a two-dimensional function, your surface is a two-dimensional function, and you only extend along the x3 direction along the normal. Okay? d alpha r3, or say, yes, d alpha r3d. I'm taking the 3D realization and I'm differentiating it with respect to one of the first two. Okay? So when I do that, I get d alpha r2d plus x3 d alpha n. And if I do d3 r3d, you just get n. Now we can construct a metric, a three-dimensional metric from that two-dimensional metric. And what we get is the following. When we contract these guys with themselves, we get something which is the 2D metric, okay, d alpha r2d times itself. We get some mixed terms, and this is what's going to happen here. What happens when you differentiate a normal vector, a vector that has unit length, is that you get something which is perpendicular to n. The space which is perpendicular to n is the tangent space. Turns out the d alpha n equals minus a gamma delta, the inverse metric, which is induced by the 2D, b delta alpha d gamma r. It's proportional to a tangent vector, and it has the curvature form in front of it. What? Can you write it larger? Yes, I will. D alpha n equals a minus sign, a metric with some dummy index beta, dummy index gamma, lower b, which is the second fundamental form, dummy index beta, the real index alpha, which came from the differentiation, d gamma r. Okay, so there are just two vectors here, and these are their coefficients. But the important thing to say is that these derivatives, these derivatives, dot the normal with tangent vectors and always vanish. It tells us that these components of the three-dimensional metric tensor are 0. And what happens if I take G33 of the three-dimensional metric? It's n dot n. That's 1. And what we end up here is the two-dimensional metric minus something which is the square of this. So I have this guy and I have this guy, and there's lots more things to it, but essentially it's minus 2 times x3 times b alpha beta. Plus, there's an x3 to higher powers here, which we don't care about. What have I just done? I just took the first and second fundamental forms and said, well, if it's a surface and it has these curvatures, I can thicken it and make it into a solid. And, you know, as mathematicians do, and we have already solved solids. So we can use that. This is a metric, 3D metric, expressed entirely in terms of 2D properties. If this is going to be embeddable in 3D space, these two will define a surface. If not, then these cannot define a surface. Yes? That's exactly what we're doing. We're actually taking a shortcut. What you suggested, the constructive proof, lasts quite a few pages. If I just try to reconstruct the surface from knowledge of A and B, I can go that path. It's somewhat more painful than this. Okay? But you could. Essentially, you could go the constructive way. I have these guys, they satisfy these equations. How can I construct my surface again? The answer is very compact, can be written very compactly. And it's the covariant derivative with respect to the metric, 2D metric, covariant derivative with respect to alpha, b, gamma, delta, covariant derivative with respect to gamma, b, alpha, delta. these are essentially two independent equations. You have one more equation, which is there is the Riemann curvature tensor induces one quantity, which is the Gaussian curvature in 2D, and that has to be equal to the determinant of B over the determinant of A. You have one algebraic equation relating different components of B and the metric tensor and its derivatives, and two linear in B partial differential equations that relate B to itself and to derivatives of the metric. Only if you satisfy all three equations. These are called Gauss, Mainardi, Peterson, Codazzi, depending on where in the globe you are. Then A and B make up a surface. Now, this is a very tedious way of stating something, which we saw in the introductory slides. I gave you B, a second fundamental form. This is the Bohemia pods. B was minus kappa, kappa. It curved in two opposite signs, in two opposite directions, into perpendicular directions, yet its metric wanted to be the flat metric. And I have a feeling that can't really coexist. This is the proof. Now, the reason we had to go through all these proofs is because from the next session onwards, we would like to start making compromises. So it's not enough for us to know that we can't do something. We want to ask, what is the next best thing we can do? And that will generate richness in the solutions, because the easiest thing you could do, you just couldn't do. Okay, so I think we're going to end here. Thanks a lot. Yes, please.
Quick question. The realizability of these surfaces, can I rephrase at least part of it by saying if I parallel transport, or if I move around on a loop on the surface, and I follow the normal, that there's a compatibility condition on the normal that it will indeed come back to itself? That the surface doesn't need to be torn or anything like that? Is that one of the things that's intuitively underlying this? If I just give you a random field of normals, similar kind of question, it's far from obvious you can make a surface which will have them.
I sort of understand what you say, but I'm not sure I have now in my mind how I parallel transport a normal, knowing just the metric.
A field of normals.
A field of normals.
It's a related question. Maybe you've already answered it. Like if I give a field of normals as a function of x1 and x2, of some hypothetical surface, what is the condition that that such a surface exists?
Say again? Yes. But it's not that trivial how you parallel transport within the metric. But that would be the case for it. There is a condition, and I think you can obtain it by taking linear combinations of this to some extent.
The next best thing might be to tear the surface?
Yes, in some cases it is. In some cases you tear the surface. In other cases you localize defects by compacting. In other cases you just uniformly distribute stresses. And the most interesting thing we'll see is that these compromises, when done in the best efficient way, will care about how big the system is. So if you try to compromise a system which is yay big, it's going to be one type of compromise. And if it's twice as big, you're going to have to find a different strategy or accumulate way more stress per unit area than you had to begin with. So these things actually accumulate in the object and not just, being solved uniformly. Okay, thanks.
Other questions?
So I guess when I look at these equations, say Gauss,
Gauss, Mainardi, Codazzi. Codazzi equations.
See, the fact that we can encode the information. Say
again? The fact that we can?
These tell me that I can encode all the information about a surface that I've embedded
in two objects.
Yeah, with just two objects that I can measure while living inside.
Not quite. So A, you can measure while living just inside the surface. If you're an ant and all you have is a ruler and you measure distances, you can measure metric. You can measure distances on the surface. You have no idea how curved you are in the third dimension. Okay, you have to have knowledge about the third dimension in order to get the second fundamental form, essentially the curvatures. It is a local property of the surface, but it only is apparent once you go out to the perpendicular dimension outside your sheet. And that is something. A clever ant that actually can go out into the third dimension could do this. Could know that the space above her is bigger than the space below her, and then it could deduce notions of curvature. But for that, it has to be able to go along the perpendicular direction.
What you said is these are local equations that sort of define the surface, but you just said you get equations that act on a global scale.
Yeah.
Somehow sense the.
So I'm saving most of it for tomorrow, but essentially we'll see that residual stress and geometric frustration lead one to the other, but are not synonymous. You can have something which is uniformly frustrated, but is non-uniformly residually stressed. So the actual type of compromise we choose turns out to be spatially dependent. And that is part of what makes these objects interesting. Thanks. No questions are stupid.
So what you did was you just added, like, you took this two-dimensional surface and you added numbers to it to make it a three-dimensional. So I was thinking, why don't you bend?
No, it was bent in the third dimension. It had some non-trivial curvatures already in the second fundamental form. It was somehow bent. What I was trying to obtain is the compatibility conditions, the embeddability of this object. And I said, well, I know embeddability of 3D objects. Why won't I use that? I could have done the other way, which is essentially just use the equations of constructing a surface from knowledge of first and second fundamental form, and I will get to the same answer, but just be a different path.
Yeah, I was just thinking about the map you showed us. So
Yes.
It was two-dimensional, and then you could just, you said nothing was removed, so I was thinking maybe we could just bend it over itself to make it 3D. I don't know if you considered a three-dimensional in your.
That I would wrap something around itself.
Yes.
So that's. It would change its curvature. If I take now a sphere, I cut it into a half, and then try closing the ends. That is going to result in a different embedding. Trying to ask if that deformed embedding, you could try to relate it to the previous embedding. But it's very difficult to deduce the existence of the previous embedding, not knowing where you're going. So what we were trying to deduce is the existence of an embedding. I give you just two matrices or two by two symmetric matrices fields, and I ask, do they correspond to some surface? And to perform most of these deformations, I would probably need to know where I started from. And this allows me to do a lot of manipulations without knowing where I started from.
Can you say relation to the you measure conformal mapping? I mean, they preserve angles but not distance.
Yes.
So why is it the conformal mappings that came up here you were not?
Oh, the conformal mapping arose naturally when I was asking questions about isotropic expansion. It was the type of deformations I was considering. I was considering conformal deformations and asking what types of them give me something which is embeddable.
But you weren't preserving distance.
I was not preserving distances. I was using expansions, large expansions here.
So lambda can be position dependent, right?
Yes, lambda is position dependent. And there's, you know.
Understand why is it then a solution? How do I understand that? Let's say in 2D, in simple case, it's actually all those functions that are conformal mapped.
No, not all the functions that are conformal mappings would give you a flat 2D embedding.
I thought that was your solution. You said any
no, it had to be Laplacian.
But that is that's the conformal map. That's the real imaginary part of a conformal map. So
yes, but not every conformal. I could. It's a function space of the same size, but the object that had to be Laplacian here was the whole function. I could cook up a conformal map that in particular would not have a flat embedding. I can conformally map the sphere to a flat sheet. Okay, that's something I can do conformally very easily. That projection, which would be conformal, would not be log Laplacian. Okay, so those are the exactly kind of functions I'm excluding. Yes, I mean, because nothing anomalous was happening at points there, it's fine. If you lose the vertex of a cone, then you lose a lot. But if you lose something on a sphere, it's kind of benign as far as we're concerned now.
So you're saying, so for example, take this function lambda, that's the solution, unique solution.
This is in 3D. In 3D, that's the only types of solutions. This is what
this solution that will keep.
That will be flat.
That will be flat.
No other solution would be embeddable in 3D. So if you try,
wait for you some non-trivial metric, but which corresponds to still zero curvature. That's what you're saying.
Yes, if it corresponds to zero curvature, it has to be this.
Well, let's think up again. So we thought it would be a good idea to have people go around the room and introduce themselves. So just a crash course on social intermixing and introductions. So maybe we'll start here and we'll go around. Because you were looking at me, you were anxious to introduce yourself.
Okay, should we just like say our names?
Yeah, so say a few words like where you come, your name, where you come from, what your interests are in physics, and what your interests are outside of physics.